So this is the aquifer that I've been working with in Oklahoma. So this is Cambrian Ordovician, dolomite, and limestone, depending on where you're at. This is actually granite. That's the bottom of the aquifer. It's bounded by some granite in the south, and it makes the aquifer cough up water and spit it out. It's called the Arbuckle-Simpson Aquifer, and that's a bit tricky because it's a driller's name. When they went from the Arbuckle into the Simpson, you're going from a carbonate into a sand that's hard to see in the drill log. It's hard to see where that transition happened, so they just lumped them together. Which makes it tricky because you go, well, okay, well, that's a big carbonate sequence? No. Well, is it dolomite or limestone? Yes. Where's the bottom? About there. So there's some innate geology things that don't quite fit with people wanting to package things. But the Simpson's on top of the Arbuckle, and drilling-wise, it's hard to tell when you got there. So I talk about this with folks around that area. It's basically your lake filled with rocks. So we think about how much water is in storage, how much can be utilized as water supply. It's used as the main water supply for Ada, Oklahoma. So Arbuckle-Simpson is the Edwards Aquifer for Ada, Oklahoma, which is about 50,000 people, so it's a little smaller. But they use one spring and 3 wells, and that's their water supply. So thinking about the properties, this one's weird. This one doesn't have a scale effect with the regional scale. As you step up from well to regional scale, it's exactly the same. And the conduits are at the bottom, not at the top. So it's funky. So the more we study this, the stranger it got. So these are the different pieces of it. The USGS renamed this the eastern piece, the western piece, and the central piece. These are the names of the structures there. This one, if you're old enough, looks about like Jay Leno. But I thought Jay Leno anticline was far better. But the town of Tishomingo is now famous because we have country music people from there. So, but this is that granite that it spits out on the bottom. And you see these sort of strong structures running through there. This is the structural trend that matches the stress field in Oklahoma. And so when we talked this afternoon about a few earthquakes, the stress field in Oklahoma results in fractures this way and fractures this way. And it's basically we're squeezing the sides of Oklahoma. And so people think about water running these sorts of ways, and then we decided that wasn't necessarily true. But those are the big structures running across there. Geologically, it looks something like this. So these anticlines are basically very different in their structure. Here's some basement popping out here. Here's basically lightly folded. Here's really unhappy rocks. And so if you go up I-35, you run up through this part and see some of the Arbuckle anticline, and you see some of those disruptions. If you go over here, it's just sort of flat-lying carbonates sitting right at the surface. This is much more limestone rich. This is much more dolomitic. And so there's these changes in this system. But this is the rock body that's below Oklahoma that we use for disposal of petroleum wastes. And so understanding this rock body in the freshwater system helps with water supply for cities and all those sorts of things. It also helps us understand what's happening with our injection zone, which roughly is one of the largest industrial disposal facilities in the world. So understanding these rocks becomes somewhat important then. So mapping-wise, we did mapping with the USGS in 3D, and so we wanted to understand what the geometry of these things were and what the effects of faulting were. We had about 3,000 well logs. A lot of them were on the oil side of it. If we go just outside the aquifer, the rocks are still there, but they're oil fields, and they're faulted down. We had about 5 seismic lines. It's 5 oil companies that made a mistake. There's not any oil in the aquifer. There's not any oil below the aquifer, but they were hoping. So thank you for your mistakes and investments. And then surface mapping. So the 3D models available look something like this. So there's the wells that were available to build this, and it was a combination of features that got it modeled. It's a lot more complicated than we thought. And if you go up in the freshwater part, you can look at the well logs. Well logs are tricky in this aquifer because they don't do much. You're like, oh, how thick are you? About 1 kilometer. Okay, so what are the big zones in the well logs I should look for? The bottom. There's not a lot there to map from. There's a few pieces, but we can look at, up top, we can look at the Simpson and divide that up nicely. And then Arbuckle Group thunk. But as we step down from the freshwater portion, you get into sulfur water, then you get down into brines. So water chemistry varies very, very quickly. You can you can probably walk from freshwater to brine wells as you cross those faults. So there's the surface of the 3D model. Tilt it and do those sorts of things. We can look at the faults that were put in there. It was very interesting thinking about modeling faults because the structural folks were trying to make the faults not violate things. And you go, well, put a line in. They go, well, you can't do that. Why? Well, it has to make physical sense. I'm like, oh, you got rules. Okay. So you can see a lot of these faults following those long structures you're thinking about. There was other ones running through here, right? So when you come up with a pattern like that, what is the correct value for anisotropic parameters? Which direction does it want to flow? Yeah, it's a little messy. Okay? And these faults, when you go out to find them in the field, they were mapped at the surface. So we've got a good map of the surface of the faults. When you take somebody out to the field to go, there's a mapped fault here. Here's the map, here's the fault. You can't see the fault. And we actually were looking for the notes from the mapping folks from the back in the 50s to say, how'd you guys map those? Because we can't see it. Now, geophysically, I've gone over several of these faults to go, is there really a fault there? And geophysically, you can see it beautifully. It shows up electrically very, very nicely as a discontinuity in this dolomite. And once you do that in certain places, you can go look between those blades of grass. Oh, there it is. But these are not obvious, and somehow they walked through this whole thing and mapped it, and we were still curious as to, how are you guys doing that? Because it's a little bit magical. When you look at the basement, let's pull up the bottom of the aquifer. There's some funkiness. So there's a 2,000 meter vertical displacement in the middle of this thing. There's Sears Tower, because I refuse to call it the Willis Tower, because I was raised on the Sears Tower. Grand Canyon is about 1,600 meters, if you can't remember that depth. So if we had a big bottle of acid in southern Oklahoma, we'd have our own Grand Canyon. But it's filled with dolomite, so sorry. But this is funky. So when you drive over the bottom of the Hunton Anticline, the eastern Arbuckle-Simpson, and you get to granite, you're actually driving off of the Grand Canyon, driving back onto land. So it feels good to me, but you're on a flat road. If we look at cross sections of this thing, there's the Sears Tower for you. And you can see how these faults affected this thing. So it's a little bit disrupted. If we look at this part's missing 2/3 of its section. And there's a geologist by the name of Eric Phillips, and he wrote to my university and the university down the road from me. And he said, I'm trying to describe that I'm not nuts. So here's all my oil company business cards through my career. He was basically the manager of lots of things. He helped design one of the first offshore platforms, which he's like, it doesn't look like we just got a drill rig off into the water. But he's like, that was the birth of offshore platforms. He was a very prolific oil man and did a lot of work in the oil industry. But he lived in Oklahoma for 5 years as a young geologist, and he wandered around this area. And he said, you know, they call the top formation above some of this stuff conglomerate, but the conglomerate's supposed to be rounded. And if you drive through I-35 and stop at those outcrops, and if you've stopped at them before, you may not have noticed this, but if you walk along there, the conglomerate is pieces that are the size of cars. And they're not rounded. And it's called a conglomerate. It should be called a breccia, and a really funky one at that. And his hypothesis, when looking at data from the cross sections and things, his hypothesis is that there was a major submarine landslide. And if you look at it, it's the size of the tongue of the ocean. So we have similar sorts of features. And we've got pieces of this rock potentially about 100 miles away to the east. And he took me out there and showed me these rocks sitting there. So we've sampled those. I still never actually processed them to see if it's the same rock. But there's a potential that there's a really cool continental scale geologic feature running through Oklahoma that has a paper published back in the 80s by Mr. Phillips. And the reply to it, they said, well, you can't distinguish this from other possible hypotheses, and it's really strange, so we think it's wrong. So if you want to end up studying giant, large-scale landslides that are continental, this might be a place to go, and if you want to get a tour, let me know, and I'll wander you through 100 miles of weirdness. Fractures, thinking about fractures. These things might be the main thing we need to study. So I'm a fracture guy, I think about fractures. So When you start thinking economically, fractures and conduits get tricky for who owns it, because sand's much easier to talk about property. Fractures and conduits are trickier. Socially, how do you manage those impacts? Which things do you protect? And I think about it this way. If we have isotropic media, it goes both directions, and I got flow going down a gradient, it's going to do that. If I got anisotropic media, instead of going that way, it goes that way. And so if you're thinking about contaminants and things and you're approximating it as isotropic, you're blaming the wrong gas station. And you can think about those sorts of issues. So we wandered around this thing, and this is some of the outcrop right in one of the stream beds. And we looked for places that there was outcrop. We walked a lot. This aquifer's not cracked at the surface. I was going to map fractures like we did with Rob Mace, and we did down in Australia. I'm going to map them. There's no fractures. It doesn't crack. I don't know why. I'm not a particularly great structural geologist as far as telling you why something cracks or doesn't crack. It's not folded enough. The rock properties are this way or that. But you can walk through this rock and you can find tons and tons of it and not many cracks. So we did find a few outcrops to quantify fractures, some of them in the middle of a stream. But then we used, we couldn't find aerial coverage of that. Lineaments have a lot of problems with bias, but we want to find out about fractures. So we did it a different way. We used streams and faults. And the streams in the Arbuckle-Simpson take right turns, take a left turn, go back this way. And so it's fairly definitively fracture control. So the streams are fairly useful for that. And then we had the fault maps. So we combined that with outcrop work and some geophysical data and try to figure out if you had a preferential direction for flow, which fracture sets do we pay attention to. So you get data like that. And that's dividing those data sets down into smaller amounts and looking at streams, which direction they go. This little block of the world, they go east-west. This little block of the world, they go north-south. And you go, well, okay, what's that tell you? Well, you got to work through it. There's your faults and analyzing those. And then we look at regional signals and we get agreement between different data sets about which direction's prominent. So we can define regional data sets. I drew this one through nothing, right? Well, that's that main data set structurally that you see running across the aquifer. That in the structure and the faults, you go, wow, it's really big southeast to northwest. Well, not in any of the data sets on the other scales. It's not an interesting data set of how the rock is broken. So we found that that wasn't much of a signal. And so when we look at that, remember that's the direction. Well, if you look at the streams, they all run against those directions that we were thinking about, north, south, and then a couple of these other directions. But basically the streams aren't following the big rough structure. It's following the hydrologic structure of how the rock's broken. And so that analysis pointed to us that, well, the streams actually know what they're doing. It's not that the streams aren't running with the main structures, it's that the streams are running with the main structures. It's just not, they're not pretty on a regional scale, it's just how the rock is broken. So this roughly north-south data set dominates the streams. The other thing that's a little weird is, this is the big one, the Blue River, about 54% of the flow. This one should be 54% of the flow. And you have a little bit of outcrop of the Simpson sandstone, and it doesn't come through it. So it ends up capping the system off, and it squirts out to the side, and it squirts out a lot here as it gets to the bottom and hits this granite. So the system is doing what the rocks tell it to do, and listening to the rocks, getting outcrop data, tells us how the aquifer is going to function. So we go to model it, we understand what we're going to be modeling because we understand what the aquifer is trying to do based on how it's built. The other one that's weird is this guy. This is the largest spring in Oklahoma, Burt's Mill Spring. The only thing it's got going for it is it's along this lineament. But the river then turns. But this is the water supply for Ada, Oklahoma. Why it's there, if you didn't have a label saying, hi, I'm 5% of the aquifer, and you wanted to point to which spring would be the largest spring in Oklahoma, you probably wouldn't choose this aquifer. And if you wanted to say, in this aquifer, where's the largest spring in Oklahoma going to be? Well, it'll be down here in the discharge zone. Because this is recharge up here and it discharges down here. So it's somewhere down here. Nope, it's up here. So even, there's still some nice mysteries in the Arbuckle. And we're still working on this one, and we'll talk a bit about that one. But this is some work with tidal work. So this is Dr. Rahi, and I stuck him out in the middle of nowhere. He had a little problem at home. I had Ron Green call me from Southwest Research. He said, "Do you need a Ph.D. student?" "Why?" Ron said, "Well, he's got a little problem at home." I said, "What's his problem?" "His home is Baghdad." This is around the time we decided to start bombing it, and he had 2 degrees from the U.S. I'm like, I'll take a Ph.D. student. So we brought him over as I ended up making him and his family the 5% of U.S. immigration that year, which was from Iraq. He's back at the University of Mustan Sharia. His family all became Americans, which is very funny. So we'll talk about that over lunch or something. But he was analyzing tidal parameters and seeing how the tide comes into these wells because he wanted to understand properties that were hard to measure otherwise. So we were looking at storativity and we were looking at how is the aquifer functioning because you can't use the well logs to say, hey, I found the confining unit because the well logs don't tell you anything. And you've got a kilometer worth of aquifer. So we use the moon as our pumping test. And we can watch the tides come in. You can watch full moon versus new moon, and you can watch the signals coming through. And so we utilize that. And you think about these things, and you've got, basically for groundwater, you've got 5 numbers you can use. You've got the M2, the S2, the N2, the K1, and the O1. For the life of me, why planetary scientists can't call it A, B, C, D, E, or at least call them something that's not this strange. And I even dug through where some of these things came from, and it still seems obscure to me, like they could have done this simpler. But those are the magical parameters of the wiggles of the that the moon instills on groundwater in the earth. So you should find these frequencies in your groundwater data, and if you do, you're watching the moon go around. So that's what we're going to look for. They get these nice names. I use the M2, the K1, and these sorts of names here. So I'll refer to those magical names. So if we're up at the top, we're going to see barometric effects and watch the atmosphere push on our wells. If we're down in the bottom, or if we're up there at the top and watching that, we'll see 2 lows and 2 highs, and that's a couple of those parameters. If we're looking at earth tides coming through, we're going to deal with confined issues. Barometric tends to be unconfined, and so you can actually use this to do aquifer type. And you go, well, why is aquifer type hard? Because we have a kilometer thick aquifer that has no properties that we can distinguish in a well log. Oh, so is it unconfined or confined? Yes. Well, how do you know that? Well, some things look confined, some things look unconfined. So where do you put the confining unit? I don't know. Let's measure it. So we tried that. So there's our data set. Now you had to use, we used, our pumping test was a transducer. We used transducers that had a 10-meter full scale. We wanted to be pretty precise, and we couldn't get enough precision with sort of standard transducers, so we went to the higher precision ones. So we did Fourier analysis on the data, figure out where the wiggles are. So identify the tides present in the data, determine amplitude and phase so that you can get aquifer parameters, get your storativity out. See if you can reproduce it and go backwards and compare it with the measurement. So this is the model of those wiggles, right? So there's a little bit up here that's not modeled so well and a little bit down here, but overall it actually matches the data pretty well to well. But that's our model of the tides relative to the actual field data. When you do that, you can see what the atmospheric signature is. We can take atmospheric data and look at that, and you get the S2 and the K1. That says I'm looking at the sky. Okay, so if you're a harmonic device and you're looking at the sky, you see S2 and K1. You don't see much else. And so it's a really nice signal that you're watching the atmosphere if you're a well. And so we get this one, and you go, yeah, okay. This is pretty weak. You get a little S2, a little K1. There's a nice strong S2 and K1. So we got a couple of these that, yeah, the spectrum wasn't so good, and you go, I'm not sure what I'm going to do with that, but you could see S2 and K1, and we didn't see some of the signatures we saw in other ones. So we could define and look at the depth of these things, and these were the unconfined ones. Some were really clean, some were a little messy. It depended on how much interaction you had at the top of the well. So these top ones could be messy, or they could be very clean. If we went down a little further in the aquifer, we'd get the S2, K1, and M2 and O1 start showing up. This one's not dominant, so it's not confined, but they're showing up. So this one sees the atmosphere and it sees the moon and looks confined. It looks like both. When you're trying to do a pumping test using a pump in a well and say, hey, am I confined or unconfined? It's pretty hard. It depends on how you fit the type curve, and it depends on how you play with the data a little bit. And you go, yeah, this is kind of somewhat in between. I'm not sure which one to call it. These data sets say, well, it's pretty easy to call it both. And we'll call it semi-confined very precisely because the data is saying it's not one or the other. It's definitely in between. Then we get to confined, really strong M2, really strong S2, and then the K1 and the O1 are going down, and we get this confined response. And so we can map around where confined versus unconfined is, but it's mostly unconfined is at the top, and we get to about 200 meters and everything gets confined. And you go, what'd you cross in the well log? Nothing. So what's confining it? 200 meters of rock. Yeah, but how's it different from what you're at? I can't hydraulically tell. So we've got a model and a concept that confined requires a confining unit. This unit may be confined by just being deep enough. And so that's a little harder for us to conceptualize because it doesn't fit what we normally think about. But there's nothing in this that says that 200 meters down is confined except for the way it responds to tides and the way it responds to a pumping test. If you look at it chemically, you go down 200 meters, you're 1/5 through this. You're looking at meteoric water with the same chemistry and same temperature you are at the surface. We've drilled to 1,800 feet. We've never found different water temperature. We've never found different water chemistry than sitting at the surface. So when you want a confining unit, this isn't the one to give it to you. This is the same stuff all the way down. And so this is telling us we get to a confined response, but we don't have anything lithologically or hydrologically to get there aside from thickness and the response. So doing the storativity, it was very interesting playing with storativity. You find that this methodology actually is more stable than other ways of doing it. But you get some numbers that are, occasionally get some numbers that are a little weird, and so you get this 42%, and you're playing with some of these numbers that you get weird numbers coming out sometimes. But 15% when we looked at an integrated data set said that was a reasonable number. So you can get some weird storage values when you work with tides, and the literature goes, there's some weirdness, and we were working on that, and we've been debating that with some other folks in the literature. But let's look at temperature a little bit. So I was telling you that going down doesn't change much. These springs that come out, they have fish, except for they have the wrong fish. They have fish from the Ozarks, a couple hundred miles north. And they look like this. These guys should be dead, but they're quite happy around this aquifer. They should be dead because they don't like hot temperatures. You guys don't find these down here. It gets too hot, it cooks them. It should cook them in southern Oklahoma, but those springs are isothermal. They run at about 17 degrees C all year long. And you go, okay, well, interesting, you have an isothermal spring. I don't have an isothermal hot spring, I have an isothermal cold spring. So we could think about their ecology. We've got folks working on that. We could think about how to interpret the flow system from that. We could think about what it means about paleoclimate. But this is a well log, and you go, well, your well log instrument's not working. Why? Well, you got colder as you went down. Yeah, that's true. So we reran it. We calibrated it. We reran it. We ran it with a different well log. We did packer testing along this thing, along our 5 or 6 spots that flowed. And you get the same low temperature. You get the same chemistry as at the top. This is an aquifer that doesn't know that depth exists, except for it's really, really thick. So there's your air temperature. You know, so we get cold. There's -10. We get hot. Here's around 30. And then there's the water temperature. And I can expand this, and I can get about 1/10 of a degree. This aquifer is so isothermal, I actually measure it with a different thermometer because your average environmental thermometer's range of accuracy is the same as the entire range of my aquifer. And I didn't realize that. I didn't realize they're like, it's within about 1/2 degree C. Like, that's my entire aquifer is about 1/2 degree C. So when you measure these things, you just get flat lines for months and months. This was sitting about that far underneath the top of the water in a spring. So the surface saw the purple line, 6 inches down at this spring, you saw nothing except for constant temperature. Those fish like that. They don't have to worry about the winter. They don't have to worry about the summer. They're isothermally babysat since the last ice age. And the biologists think that since the last ice age, they stayed there. Everybody else died as it got warmer, and you have to go up to the Ozarks to find those fish again. So they have a little environment that's put there by the temperature that they're living in. If you map that, this side's a little warmer, this side's a little cooler. This is where that Simpson sandstone's sitting on top of the Arbuckle dolomites. And so in order to get this to happen and get this to happen, if you look at this sandstone, it's fairly normal sandstone. It's layered, it's got some fine things, it's got some coarse things. It's horizontally anisotropic, like we normally think about rocks. Yeah, okay, rocks, it's usually 10 times harder to go up and down than it is to go side to side as a first guess, because you got layering. This dolomite, even in the groundwater model, we couldn't do it without vertical anisotropic conditions. That going up and down is easier than going side to side. And so here you can go up and down. Here you get stuck underneath that sandstone and it gets a little bit warmer. And you come out here and you're cold. And that's where those fish like to live. So this is their little site. They have this constant water coming out at a constant temperature, and they're quite happy there. We can look outside the aquifer and you get something called a geothermal gradient, right? And so your gradient's about 18.3 degrees C, and it's going down and things are normal right outside the aquifer. Right inside the aquifer, things aren't very normal. They're isothermal. And we really struggled because we're like, this data doesn't make any sense. Why? Well, you're supposed to have a geothermal gradient, and all we do is get a little colder. So we struggle with that a bit. But here's a model. This is a model of that aquifer is vertically conductive hydraulically, and water goes up and down through it, except that you've changed the surface temperature by 0.4 degrees C over the last 50 years. If you do that, that models the aquifer quite nicely. So global warming signature of 0.4 of a degree C makes a nice thermometer change measurement, and you've sent that change down this far, but otherwise you have something that has circulated water vertically very, very well throughout at least 1,800 foot of the aquifer, and you're just flowing up and down better than you're flowing back and forth. So you get a little bit of a weird system that makes fish quite happy. Now, the other thing we're doing in this aquifer, I had a client commercially. This guy used to work for Raytheon. He worked with the environmental cleanup and management of explosives. So you've heard of C4. He worked with all the ones you've never heard of and the environmental impacts and making sure you kept things clean. So when he went through airports, he's one of the first people that, you know, when you get swabbed, he was the first one to test those protocols. And he hasn't been arrested. So he comes to me and he says, I'm a professor now. What are you in? Fire safety. What do you do? I burn stuff. Oh, great. I like this. He says, you know, I was one of your clients. I'm like, yeah, okay. So what do you need me for? He says, I need a Ph.D. We don't have Ph.D.s in fire safety. We need to get one of those. I'm like, oh, okay. He says, how about if I do one with you? I don't burn things. I like to burn things, but I don't burn things. So he was a gas expert. What I was going to look at him with was gas coming in from environmental sites into basements and into buildings, right? Because he can measure gas really well. I do groundwater stuff, and so we thought we'd do that boundary. Turns out those sensors are super expensive, and neither one of us is listed as an expert in gas coming out of groundwater and going into a building. But gas comes out of springs too, and I said, you know, I know you guys know tons about gas. I don't think we as groundwater folks know tons about free-phase gas. I know we write about it. I know we sample it for age dating. I know we sample it for chemistry. But I don't think we know a lot about it on a physical basis. And so we did a paper looking into it, and he says, yeah, you guys don't know anything about gas. I'm like, great. So what we looked at is, why are bubbles significant? Why is free-phase gas important? And you got things like Lake Nyos. You can kill people, have bubbles come up and just kill people. And so this lake burped up CO2, and about 1,250 people that were sleeping kept sleeping. You've got methane and phosphine. Those are ignitable, so you can have people that are getting blown up by bubbles or getting killed by gas coming out. This is the fire swamps from Princess Bride. That was a great demo of groundwater processes. So there's your fire swamp issue. Contaminant transport, you can have ebullition. You can have alteration of phase, dissolved phase gas measurements. And this is one that Rob thinks is pretty important. We were looking at age dates in the Arbuckle that the USGS did, and we think we see a gas stripping signature, that air coming through the groundwater is stripping the deeper signatures people are using to date the groundwater. And he feels like he could probably throw out about half or more of groundwater age dates by demonstrating air stripping effects. So we're working towards that, of getting rid of half the groundwater age dates. So if there's one that you don't like, let us know. We'll tell you if you can throw it out. But he's working towards that. But we had to think about how to measure it and how to quantify it. But he's thinking about, well, what's it going to tell us about groundwater to look at free phase gas? It'll tell you about how's it coming out of the ground, because you can't get gas out of certain situations and bubbles only work certain ways. It'll tell you about the pathway it took to get there. And it'll tell you about where the fluid came from. So there's a lot of things gas could tell us, but typically we only do the chemistry. We don't do the physics of the gas. So if you're in the Bird's Mill Spring, if you go underneath it, it's actually an upside down bridge deck, and it's protected to protect that water supply. And we sneak in once in a while and do some experiments. What's cool about this is if you've got a bucket list of groundwater, you can add this one. This is something you've probably not done in your life. There's enough bubbles coming out of this, of air, that it's actually pressurized as a spring box. And so when you go down in there and are breathing and don't die, which I encourage my students not to do, you're actually breathing groundwater air. You're not breathing atmospheric air, you're breathing air that went through the aquifer. And there's not a lot of chance you get to do that of a spring providing your air to breathe while you're looking at it. So if you want to check that off on your bucket list, there's one spot that you can go breathe groundwater. And it's about 19% oxygen, so don't move too fast. And basically it rains bubbles out from the bottom of this thing. It's kind of this really cool thing of just watching these bubbles raining out of this thing. But we were trying to figure out what's the best way to organize gas phase data, and we found that there wasn't organizational methodologies. There were people that measured things and people that wrote about things, but there wasn't a good way to organize it. First thing we found is people use language about bubbles really badly. So there's gas and steam versus vapor, and that's relative to boiling point, and people use them interchangeably, but they're not. This is the one that makes me crazy on springs, is everything's a boiling spring, but almost nothing is warm. It's actually churning is the correct term. So if you're talking about springs that are roiling and things, they're churning, and if you guys could use the language properly, they're not boiling. So we find that in the literature a lot, that things are boiling when they're not actually hot. They're actually churning. So I had to start making myself say churning after working on this for a while. And then dissolved versus free phase gas. If you're dealing with the physics of gas, those are hugely different. If people are sampling gas, they're like, yeah, so it's bubbling. It's like, no. You've got the phase change going on, and you're taking a measurement where you're going to quantify something, except for you didn't quantify that you had multiple phases going on. That altered everything. So did you at least keep track of which ones were free phase and which ones weren't? No. Okay, well then we don't know what your data actually say. Well, yeah, we do. We measured them in the lab. Yeah, but you don't know what you sampled. So this is the one that he's eventually trying to poke out, is dealing with that issue. So we ended up with 7 categories for free phase gas coming out of groundwater. 7 things that we said, yeah, and we bounced this back and forth. We bounced this back and forth across people in the discipline, different people, and trying to figure this out. We came up with 4 shallow and 3 deep mechanisms. We named them for the process, not the composition, although composition is pretty indicative, a lot of them. And the different facies that we called them, they might overlap or mix. You might have more than one gas phase come out. And we used, we ended up with these 7. And we went to publish this, and Rob was ready to publish. I'm like, I'm not sure it's ready. He says, I'm ready. And so he got rejected, which was a good lesson for him. And the rejection came in 2 forms. One is, this is still too confusing for me, and I think you could do these things, and I would look at these references. And another reference that said, this is useless, there's no reason to define this for groundwater. And I'm like, well, but we need some way to talk about gas in an effective way, and saying gas came out. I got gas coming out of Yellowstone, and I got gas coming out of a spring in Oklahoma. Those aren't the same gas. So we need to define this somehow. So it is useless for some people. We're finding it useful as a language. So we have swamp gas coming out. We've got air entrainment that it comes in a car system, gets air stuck in there. Bernoulli, that it's squeezing out air, and you're getting mostly nitrogen. And then soda springs, you're getting mostly CO2 coming out. And we've got a paper coming out on this. It's online. This is the figure that's going to be the cover of Groundwater in, I think, November. And we actually had one of the art professors that we drink with. She helped us draw these because we were really terrible at drawing nice block diagrams. So she drew nice block diagrams for us. And so we got her on the cover of a magazine with her art. And she was not impressed, but I told her she should be. But these three would be something coming out of a hydrocarbon or a coal producing methane. Hot springs where you're getting some thermal signature that's coming up that you're basically boiling it. And then mantle bubbles and thinking about deep gases coming up, usually helium and things. So these 7 comprise most of the literature we can find on this. And he used about 120 different references on gas and groundwater to come up with a way to categorize it. So Arbuckle are these sorts of guys, air and nitrogen coming out. That's why we can breathe inside that tank and we can use that. But he decided, there's Rob. There's Rob in the field, so they look a little different. So Rob built the Bubbletron 9000. We're looking for a nice acronym. I don't think we found it yet, but it was named after some video game instrument of death, and he named it the Bubbletron 9000. So we've got this shroud. This was the first attempt. You put a shroud over this thing, you pull the gas off, and then you send it through. You have to dry the gas first. You need power supply with a solar panel. You dry the gas, and you send it through, and you measure the mass of the dry gas. Okay, well, how'd that work? Well, it's destroyed immediately. So he's related his project to being the swamp castle king from Monty Python, that he built the swamp castle, it sank into the swamp. He built another swamp castle, it sank into the swamp. But it turned out we had floods that we didn't know about that came through. And you went from 1.1 cubic meters per second in the stream to 283, and it took out, this used to be a solar panel about 10 meters away, and then the water level inside of his magic box filled up to about there, which was only the depth of all of his instrumentation. Yeah. And once you do that, there was enough power to send the water through this thing that was really expensive and destroy that too. So, so he built another swamp castle and put him up in the trees and did all sorts of things. But he eventually got one built. And so this is a hydronomograph. So this is blue, it's the water phase coming out. And we're going to talk about this at GSA in some more detail. Green is your gas phase coming out, measured every 15 minutes. So we've defined the different types of gas. We've defined that we can measure it. We've also defined good luck understanding it. So he's now working on that. We're working on the steady state. So a reasonably steady state in the water. And you can see here where the water kicks up, the gas kicks up. See, nice and correlated in phase. And then here again, water kicks up and, oh, the gas kicked down. Here the water kicked up and the gas did all sorts of things. And he went through lots and lots of iterations to get to a clean data set. This represents months of work to get 4 days of goodness. He's got more goodness in 4 days, but the things we learned is that if sun is hitting your shroud, you will affect your gas measurement dramatically. If the trees are pumping and stopping and doing things, they'll affect what's happening. So trees turning on and off in the winter, you could watch that happen in your gas and your water, that the trees turned on, the trees turned off. There's lots and lots of information in the gas phase. There's not much data available, but this is a data set of how much water came out of the hole, how much gas came out of the hole. He's thinking now that using a little spring that has gas coming out quite well and this little spring coming out, I mean, we're not talking about a huge flow here, might have been wrong. Maybe we should have gone to the big box that's blowing gas out with lots of water and try to look at that signal. It might be easier to measure. I'm not sure that it's going to be easier to understand. But I think there's a lot of data in here that is obviously a different signature than the spring hydrograph. And it's telling us things. And he's got hypotheses he's testing. Some are not working, some are. But his third paper is going to be telling me what this means. And it's quite interesting. What's happening is the amount of gas here, we're just doing steady state to start. The amount of gas coming out is too much. If you go, okay, you dissolve the gas, you recharged it, and you went through and you came out, you can't get that much gas. So he knows that you got to be recharging free phase gas somehow. If you back out a recharge temperature out of this data set, you get 18 degrees C. But we know that that's not the recharge temperature of this aquifer because it's isothermal. So he's finding that if you have the gas phase data to integrate with, you can disprove a lot of hypotheses that people hold up quite dearly because they have no data to refute it. So we think this is going to be useful to measure more gas in springs. We think it tells you a lot about the aquifer. We're not sure what it all means yet, but we can tell you it's hard to measure. His instrumentation went from that box that flooded to all sorts of circuitry and spare drying things and controls and extra things to prevent damage. So it's pretty Rube Goldberg now. So if you go, hey, I'll go do that, I'll go measure gas out of a spring, give Rob a call. After a 30-minute conversation, you may decide you never want to measure gas in a spring. But it can be done, and I think there's a lot of information that being physical about it, what quantity is coming out, and then keeping track of the chemistry. So we had the USGS do the chemistry of the air, and we see very interesting things because the hypotheses that they make based on their chemistry and backing out dates are inconsistent relative to the physical amount coming out. So we think there's going to be a lot of things good coming out of that. A lot of folks helped out at various parts, including Liz, the art professor. And if you ask her to draw something for you, she may say no, but let me know and I'll get her a couple of drinks and we may change her mind. But if you have any questions on the Arbuckle-Simpson, let me know.
The preceding program was brought to you as a community service lecture by the Edwards Aquifer Authority. For more information, visit edwardsaquifer.org.